I'm glad you're here. Would you like to introduce yourself a little bit, please?
I'm Nicolas Fränkel. I've been a developer for 20 years. A couple of years ago, I went to the developer advocacy path. I'm mostly a Java developer. Now I prefer Kotlin a lot more. I started to dabble in Rust. I'm interested in about a lot of stuff, and the talk is about one of them. That's how to leverage some technical tool to implement a feature that you might be interested about.
Okay, cool. Yeah, I would say we will hit the talk now, and just as an information for everybody, the talk is pre-recorded. We do not make a secret about it.
Chromecasts or cast-enabled TVs linked to your account.
Okay, that means that everything you hear is already pre-recorded. We are in the chat. We will look out for questions. We will collect the important ones and interesting ones. And at the end of the talk, we will be back in here. And you have time to ask questions and interact with the speaker. Have fun with the talk, and see you in a while.
Hi folks, thanks to be here for this talk about the change data capture use case, designing an evergreen cache. I'm Nicolas Fränkel. I'm a developer. I've been doing Java development for 20 years. A couple of years ago, I learned Kotlin, and right now I'm trying to teach myself Rust. I'm also a developer advocate, and I work for a company called Hazelcast. We have a product simply named Hazelcast, and it has two main capabilities. The first one, it's in-memory data grid, and you can think about an in-memory data grid as a way to store your structure across several nodes, so you can do replication and sharding. And the other is an in-memory stream processing engine. I will be using them in the demo, but you can replace them with any technologies that you are used to with the same capabilities. This is our agenda for today. So the first question I want to answer is, why do we cache? Because sometimes I hear that cache is bad, or you should never cache, or you cache because you design your system badly. This kind of questions, I first want to let's say answer them. Then we will see some alternatives to keep the cache in sync with the source of truth. Then I will tell you about one way which seems right now to be the way, and it's called change data capture, and I will try to explain it a bit. Then we will see Debezium, which is an implementation of change data capture, and then we will see how Hazelcast and Debezium can work together, where in places where Debezium itself alone is not such a good fit. And finally, I will do a demo. As I mentioned, the first question I want to answer is, why do we cache? And the answer is because of two main reasons. Sometimes you want to cache because you prefer fast data that might be stale instead of slow data that is correct. And the other reason is that sometimes you prefer data that is, again, stale, versus no data at all. And in both of the cases, you can imagine microservices. So imagine you have an e-commerce application that is designed around microservices, and microservices mean distributed, and distributed mean network latency. And this e-commerce application has a checkout microservice, payment microservice, a pricing microservice, a catalog microservice, a card microservice. Well, really a good, nicely designed application around microservices. And now imagine a customer, and they want to go to the checkout, so you call the pricing microservices to know the price of the cart. And at that moment, there are two ways that it can go wrong. Well, the network lags for any reason, and it takes a long time, and you might know that customers, they don't like waiting, so they might decide to go away, which is not great, or even worse, the pricing microservice for whatever reason is down, or the network is down, or whatever, and you've got no price at all. And in that case, the business will always prefer to sell at a slightly wrong price than not to sell at all. And imagine that at the end of the day, sometimes you will sell a bit too high, sometimes you will sell a bit too low, but in the end, everything will be average. So on average, you will have sold at the right price. And again, you will have sold. And in e-commerce, for example, this is very important. So the main trade-off of caching is that on one side, you accept stale data to get speed or like data. And there is nothing wrong with caching as long as you understand that it's a trade-off. As an example, I have here a very simple system. I have an application that reads and writes to a database, and between the application and the database, I have a cache layer. So the cache acts as a facade. So every time I write to the cache writes to the database, and so my system is always in sync, and I'm very happy. But unfortunately, this situation occurs very rarely. Most of the time, what will happen is that you've got a third-party component that will update the database regardless of the application. And in general, those are reference tables. So you might have a registry of customers or a registry of countries or anything, and you want to have them up to date. And the problem is that if the cache has already been loaded with those references, you can like update the records in the database, and the cache won't reflect those changes. So the main problem is, how do we keep the cache in sync with the database? And you might have come upon this quote that there are two hard things in computer science: naming things, cache invalidation, and of course off-by-one errors. And one of the way to keep the cache in sync is cache invalidation. And I need to, let's say, define some semantics. You might also have heard about cache eviction. So you have, on one side you have cache eviction, and on the other side you've got cache invalidation. Those are two different things. In the end, you will remove items from the cache, but for two different reasons. Cache eviction first. So imagine you have been tasked to do something, and you say, oh, caching is a good idea. In general, if you are a young engineer, and I've been in this case, you will say, oh, I will use a hash map, or depending on your language, it might be called a dictionary, an associative array, or whatever. And that's a very bad move, because whatever data structure you call it, I will call it a hash map because I'm a Java developer mainly, and in Java it's called a hash map. It's unbounded, so you can put like entries in it and entries in it and entries in it, and actually the memory consumption will grow because the entries, they are never removed. So the first thing you need to do is set a limit on your cache. You have a cache size. You can use any caching provider, be it Hazelcost or anything else. They will always provide you with those capabilities, because using a hash map is easy, and now designing a limit and designing all capabilities around the cache is much harder. So please, be nice to yourself. Just use an existing cache provider that provides you with those capabilities. Anyway, now you've set a limit, and imagine you have put entries into the cache, and at one point you will reach the limit, but still you will need to put one more item into the cache. And the question is, which item do we remove? And this is cache eviction. And cache eviction has actually multiple strategies. You can have like list frequently used, list recently used, you can have dedicated priorities, you can have plug and play strategy, whatever. This is cache eviction. You remove entries from the cache because you want to put one more entry to the cache and the cache is already full. But there is cache invalidation. And cache invalidation is bound to the idea of time to live. So when you put an entry into the cache, you need to think about how long will this entry be valid until it's removed by a background thread, so that the next time you ask for this entry, the cache will be empty and you will need to go to the source of truth. And that's how you keep the cache in sync. You will put entries, you will say, hey, they will live there for 5 seconds, for 10 minutes, for 2 hours, I don't know, it depends a lot on the context. And after that time has elapsed, the entry is removed, and then your customer, your user of the cache will go through the cache, notice there is nothing there, and will go to the source of truth. And as I mentioned, it's one of the hardest problems. What's the correct time to live? What's the correct length of the cache invalidation? And let's think about our batch issue. That we have a batch that runs every hour and that writes to the reference table. And we want to keep the cache of the reference table in sync. So it runs every hour, and we have a TTL of half an hour. That means that every half an hour, the cache will be cleared of those items. And the problem is we will go to the database, but after 30 minutes, the batch has not run, so we will actually be wasting resources going to the database and fetching the same data as was before in the cache. On the opposite side, if our TTL is 2 hours, that means that during a 1 hour window, we will be reading from the cache and actually not using the data that was refreshed by the hourly batch. So we could say, oh, let's put it just at 1 hour, and it seems like a good idea. But again, we are thinking about distributed systems. So there is no way to actually synchronize a clock so that both the cache and the database and the batch, they have the same clock and they are synchronized. Even worse, that doesn't work at all, because actually the cache won't be containing all the entries. What will happen is that the application will need to access one record of the database, will try to get it in the cache, then it won't find it, it will go to the database, it will fetch it, put it into the cache. And 5 minutes afterwards, we will need a new record, so that it's not a bulk put into the cache that we need to do every hour. It happens like when we need it. So there is no way to have the correct time to live. And so we must guesstimate, 5 seconds, 10 minutes. Again, it depends on your context. And it will be always hard to come up with the right time to live, because on one side, again, stale data, on the other side, like overconsumption of resources. And now we can think, okay, so instead of having those scheduled, we could be event-driven instead. And that fits our use case very nicely, because that means that if no changes happen, then we do nothing. And as soon as we've got a series of change happening, well, we will fetch the data. And if I'm telling you about event-driven and about databases, if you have got a bit of experience in databases, you actually think about triggers. Triggers are just the way to do that. Well, there are a couple of problems with this approach. The first one is not all SQL databases like implement triggers, but even if one does, triggers are actually meant to do stuff on your own database. So inside the database, you will have a trigger that changes the data in the database. But here, we want to synchronize something that is outside the database. We want to actually call an external process. So how does it work? Well, I've come up for this talk, I did a bit of research, and I've checked the example of MySQL. MySQL implement triggers, And with MySQL, you can actually call external processes with a trigger. It's not all unicorns and rainbows. Actually, you need to write a function in C++. I don't know about you, but C++ for me was when I was 20 years younger in university, and I don't really want to do that. But anyway, you will have an expert C++ developer, and then there are constraints on the operating system. There are constraints on how you manage SQL. Well, it's possible, but it's not fun. And actually, there is already an existing lib that does it for you. So there is a person who created a generic library to do that. So you only need to come up with the command that you want here. It's a concat something, but you don't care about what it does. And then you have this sysexec library. You just need to call your command, and it will call an external process. I didn't check if it's still maintained. I didn't check if it's buggy, but at least it's something that you can start using and check how it works. Now, if I put on my architect hats, well, I have some problems with that approach. The first one is implementation dependent, meaning, hey, it's good because MySQL does it, but if you have Oracle, if you have Postgres, or worse, if you have like different databases in your information system, it will be very hard to come up with a solution for every one of them. Then it's fragile. I mean, you have so many moving pieces that it's gonna be a mess. And it's not, if it breaks, it will break anyway. At that time, who will debug it? Will it be the developer? Will it be the ops team? Will it be the database team? It will be hard. And organizational issues such as this, we better design them before the problem happens. And the chain is so wide that it will be an organizational issue deciding who is the proper, who is the proper team responsible for that. And if you have done trigger in the past, you know that if we trigger the trigger too often, it will be very, very resource consuming. So it's time for me to introduce change data capture. Change data capture, you got the definition here on Wikipedia, but actually I will define it in a way, in opposition to event sourcing. You might have come upon the term event sourcing. And the idea behind event sourcing is actually that you store the events in your data store, and when you need to get the state, you will replay the events one by bit. So if we start with, let's say, a bank account starts at a balance of zero, and then you have events, you have credits first, I hope so, and then you've got debits. And then if you want to know the balance of your bank account, you can replay the events. And of course, the biggest benefit is that you can check the balance of your bank accounts at any point in time because you've got all the steps that led to this balance. This is good, but of course, with legacy system, it's not possible because you need to redesign the way you store your data in a completely different way. Also, because the number of events can be very, very huge, you need to take snapshots at regular intervals so that you don't need to replay all the events from the beginning of time, but perhaps the 5th or 10th or 100th latest events. And change data capture is exactly the opposite. With event sourcing, you create state out of events, you compute state out of events. With change data capture, you create events out of states. That's how I like to define it. And actually, you might have done already change data capture in the past. If you had a database and you had a job, a scheduled job, and in this database, you run this job, and based on a specific column with timestamp or version numbers or status indicators that you afterwards updated, this is already very similar to change data capture. Triggers, I mentioned them. Triggers are also a way to do change data capture. But the current way, I wouldn't say the easiest way, but let's say right now the way that provides the most benefits is actually using log scanners. What are log scanners? I'm glad you asked. So you might have come upon this article by Martin Kleppmann, turning the database inside out. And in that article, he makes the case that if we redesigned the database nowadays, it would be like not very different from what we are doing right now, but actually we would like completely like decouple the symbolic architecture, the symbolic engine, and the physical architecture. So it's quite similar to what we are doing, but when you are a developer, and especially again in the Java world, because it's the one I'm most familiar with, when you need to interact with a SQL database, what you need is like the user, the password, and most importantly, the URL of the database. And the fact that this database is as a leader-follower topology, you don't care. It's just assume that it will work as it is. And then in between, you have network and direction, whatever. So if the leader fails, the follower will take his place, the application will continue running. And now from the upside, it's completely different because we actually need to implement this leader-follower approach. And more importantly, what we really require, if the leader fails, the follower will be in the exact same state that the leader was when it failed. And for that, most SQL database management system, they have a so-called log scanners. So what happens is when the leader receives a SQL statement that will change its state, like an insert, a delete, or an update, or even a DDL, then what happens, it will write it down into a dedicated write-ahead log, an append-only log. And then afterwards, it will read this file to apply the changes. Meanwhile, the follower will do the same. And because this log scanner is unique, the leader and the follower, they will execute the statements in the same order because it's a write-ahead log, it's an append-only log. And so at the end, after some time, it's expected that they will be in the same state. So reason for this log is replication. It's also data recovery, meaning that the first thing it does, if there is no such thing as a leader follower, if there is a single node, we can still use the log because we will write first into this file. And if any process fail, then we can restart the node and it will read from the file so we don't lose anything. So now that I have explained that, perhaps there is an idea coming saying, hey, what if we hacked this log? And it seems a pretty good idea. Because now, again, taking the example of MySQL, this is what it looks like. And actually, we can see that here there is an update where set. So this is pretty understandable. And of course, there is some stuff that is not understandable at all. It's very specific to MySQL. It's not SQL itself. It's just an implementation detail. And you might object, hey, before you told us it's not implementation independent, sorry. It's fragile, of course it is, and who will maintain and debug it? And those are very, very valid points. So, what can we do? Well, there is somebody or someone or like an organization, a library that does it for us. And it's called Debezium. And Debezium actually acts as an abstraction layer upon those logs. So you've got a nice and clean API on top of that. It's provided by Red Hat under the friendly Apache v2 license, so you don't need to pay anything. And at its inception, the idea was it would be very, very embedded into the Kafka ecosystem. So whatever would happen to any database that it supports, MySQL, Postgres, whatever, then the Debezium would like capture the change and would write down some stuff into Kafka topics. And in sometimes we don't need Kafka. That's, I think, a problem of the industry right now. We have Agile, we have microservices, we have Kafka, and we need to use them because there are many successful organizations that use them. So if we use them, we will be successful as well. Sometimes Kafka is not the right fit, and especially for a cache. So we will have a database, we will have the cache in memory. If we put Kafka in between, it makes no sense. We would like gladly just have directly the changes from the database to the memory and without any broker. Anyway, right now at the time of this talk, Debezium supports already a number of connectors to several databases, and of course MySQL, Postgres. You can see those are not only SQL databases. For example, it supports Mongo, it supports Cassandra, or it's incubating, and yeah, there are production-ready drivers, or connectors, I should say, and there are incubating one. If you're interested, you should regularly check if your database is supported, or of course, you can create your own. Now, I will just like very fastly introduce Hazelcast. As I mentioned, we have two capabilities. The first is an in-memory key value store, in-memory data grid. The second is an in-memory stream processing engine. It's distributed by design, and again, it's licensed under the Apache 2 license. So the idea is you've got a couple of connectors on the left. You can read from a variety of sources. If something is not there, you can create your own. There is an API to create your own. And then on the right, you can dump the data to anything that we support. Again, if there is not something that fits your fancy, you can write your own. And in between, you can do some transformation, combination, enrichment, whatever. And yeah, this is a data pipeline as you know it. And we support multiple languages, of course. We actually have two deployment models. Since Hazelcast is developed in Java, the easiest way is for Java developers, and in that case, it's used as a library. So you use Hazelcast as a library in your Java application. When you start your application, you start the Hazelcast node. The node, there is an auto discovery process, so it will find other nodes and they will form a cluster. That's great to start with. However, of course, the nodes and your application, they will run in the same JVM, so they will compete for memory. And if you start relying on Hazelcast as an infrastructure component, that's perhaps not the best way to do that. So we have another deployment model, which is the client-server mode. In that case, you have a dedicated Hazelcast cluster. Again, auto-discovery will provide Docker images, Helm charts, whatever, or you can run it like directly with a shell command. But in general, like our user prefer to use some kind of containerization. And then you have your application that are clients of the cluster. And in that case, the really good thing is you're not limited to Java. You can use any of the SDK that we provide, including Python, C++, Go, and Node.js. And I forgot C#. The way to do a stream processing engine, actually all stream processing engines are more or less those two concepts. Here I'm using the Hazelcast semantics, but if you are using another stream processing engine, it will be the same concept, just different words. The first is we declare a pipeline, and the pipeline is where we will be reading from, what steps we will apply, transformation, enrichment, whatever, and where we will be writing to. And in Hazelcast, we declare it through Java code. Then when that is done, we package that code and then we send it to the stream processing engine through a client. When the stream processing engine receives the code, then it gets the pipeline and it starts like executing it, and then it becomes a job. And because it knows about the topology of the cluster, it can send it to the different nodes and it can orchestrate the flow. Now let's get back to our use case, because now we've got all the pieces that we need. So we still have our application that writes to the cache, we still have our database, and we still have this component that behind our back writes to the database, and then back to the problem at hand. How do we keep the cache in sync with the database? What we will be doing, we will be having a jet job, and actually the jet cluster, the cluster will be a single node that will, every time there is a change to the database, it will capture the change and it will write down to the cache through the cache API. Well, I've talked a lot, and now I believe that it's time for some coding. So here I'm in IntelliJ, I've already written the code, otherwise it will be a bit too long. And I have an application, and this application is actually a Java application. I'm using Spring Boot, but it's not very important in that case. And the idea is that I've got a couple of dependencies. First, I'm using a web application, so I have all dependencies to create web application with Spring Boot. I have the Spring Boot starter web, the starter time leaf. I will be using some jars on the front end, so I'm also using web jars because I don't want to add the dependencies in NPM. Then I will be interacting with the database, so I have the Spring Boot starter data.jdbc, and I have here two different dependencies, two different databases. The first one is when I'm running completely isolated, and here I'm using SQL, MySQL. When I'm running deployed. Of course, I will be using Hazelcast to have some cache, and let's run this application. So I will run the application, which is called demo application, and meanwhile I can show you the code itself. So I have a controller, and the idea of this application is I want to manage persons. And persons is quite easy. Person has an ID, of course, a first name, a last name, a birth date. That's a very simple demo application. And I have a controller, and this controller allows me to display all entities from the database or to update a single one. And I'm using the repository, and the repository does the following. So the repository will use the Spring's JDBC template and will actually use two caches. The first cache, I will put the entities themselves. The second one will put the query. So if you know about Hibernate, this is very similar to what Hibernate does. But let me explain, because I redid everything from scratch. When I want to find all the entities, I will first define the query itself. So I will select all columns from the person table, and then I will check in the query cache if there is already a key with this exact query. And of course, at the beginning, the cache is empty, cache is cold, there is nothing. So if it doesn't find anything, what I will do, I will execute the query. So I will get all the data from the database, and for every entity that I find, I will put that in the entity cache. And afterwards, I will put the query itself with the keys. So the key will be the query, and the value will be the ID of each person in turn. Otherwise, if the statement, if the query has already been found into the cache, so after the second run normally, then I will get each of the keys, and I will get the keys from the entity cache, and I will return the collection. Now, when I want to save a person, I will just put every one of them into the entity cache directly. This is how it works. So here I'm running locally. I'm using H2, which is not very interesting because I have an in-memory cache in front of an in-memory database, but it's just to show you how it works locally. Here I have done a fetch automatically, so I've got all the entities. Of course, I can refresh I will get the same results that's expected, and I can like update one row. So it will save that into the database, and it will actually like reload everything, and all entities will be reloaded at that point. This is how it works locally. Now what I want to do is I want to deploy that in production using another database. So for that, I have a Docker Compose file. And this Docker Compose file is composed of these applications that I have containerized. I have containerized it through Zip, but that's not very interesting. Actually, I will be like providing you at the end of the talk on the last slide with the GitHub repository URL, so you can do it at home. Here I have the pipeline that will be keeping the cache in sync. For now, I will deactivate it because I want to show you the problems that I have. Here I have management centers. We have a management console. So far, everything that I've shown you is open source and free. Management Center is actually free, but not open source. If you have, I think, no more than 2 nodes on your cluster, so I won't show it to you. And then, of course, now I have the database. And now what I want to do is I want to do the Docker Compose app. So I want to start the application in like this, like production mode. Let's wait a bit. And now I want to stop the pipeline because I want to show you the problem first. So I will just Docker Compose stop pipeline. Okay, now let's see how it looks. So I'm still running on localhost 8080, but now I'm using Docker. And I have Roberta do, Corinne do, and John Rowe. And so let's say that here I want to get back to Johnny. I will update it, and amazingly it works. Now I don't have any batch job that does something under the cover. I have created a dedicated application for that. So I will be using this update application. It's a Spring Shell application. And actually, it's not very hard. I will just be updating the database directly. So I have a couple of commands. The first command is list. It gets me the state of the database as it is now. So you can see Johnny, my latest change, Corinne, and John. And now what I will be doing, I will be updating the first row with Robert. And now if I get back to the application, and I refresh, of course, I still have Johnny because this application is reading from the cache. There is no way it can work. And so we have this problem of the cache not being in sync with the database that I've talked about a long time. So the idea is now we can start the pipeline. And with the pipeline starting, Docker start, Docker Compose, start pipeline. And meanwhile, I will show you the code of the pipeline itself. This is actually pretty straightforward. Here, it's a simple application. There is no Spring Boot or whatever. It's supposed to run completely in a batch, well, not in a batch mode because it won't stop, in a pipeline mode. So we will start it and it will run until we stop it. And it just relies on Hazelcast itself. And this is the ID. We've got a main class, a main method. So the entry point, there is no framework or annotations or whatever. It's just simple Java method. And then we will create this new jet instance with a new job of the pipeline. And the pipeline itself, it looks like it can be read in plain English. The pipeline is read from the database. We don't care about the timestamp now. Peak will be writing things down in the log just to check that everything works. And then we map the results to a person and then to a map entry. And then we write to the cache. And of course, we can check what everything does. So the database methods, what it does is is just uses one of the primitives of the Hazelcast API, and it's just configuration. So the idea is that it should work in most cases. So if you deploy it into a container, onto a platform, as a container, then we can replace the MySQL host, the MySQL port, the MySQL. It's just configuration, not very interesting. So that is pretty simple. And we write to the cache. Again, we will just be connecting to a remote cache. So we have two different Hazelcast instances running, one for the application that just managed the cache, and the other is just for the job. So the job will connect to the first one. And then again, it's just configuration, and we just need to know the name of the map that we are using. Let's get back to the application, because now the job has started, and if we just refresh now, I will be just refreshing, we can see that, hey, Robert is here, so the cache has been updated. And so we caught the changes that happened before the job started. That's really cool. But you might say, oh, but it takes a lot of time. Not at all. But now what can happen is that every time we do a change, so update to Chiara, and if we refresh, then we've got the changes every time. So of course, it's not supposed to be instant. We are talking about distributed systems. So there will be eventual consistency. The idea is that the window where the data is not in sync with the database is very, very small. And this brings us to the end of our talk. So recap, in this talk, I've shown you the caching trade-off. The caching is not bad per se. It's not a smell. You shouldn't shy away from cache. You should understand that it's a trade-off between, hey, we accept stale data, but in exchange, we've got either like available data or fast data. And in some cases, it's better to have available data or fast data than correct data. But this trade-off, we can, let's say, manage it in a better way by using change data capture. So again, stale data is not that great, but the time when data is stale, we can reduce it to a bare minimum if we think about using event-driven a system, and in that case, change data capture. So Hazelcast and Debezium play nice together to provide you with this. Thanks a lot for your attention. You can read my blog, you can follow me on Twitter. As I mentioned, if you're interested in the repository itself, everything is on GitHub under bit.ly.evergreen-cache. And if I got you interested by Hazelcast, in any case, join our Slack and get free training. So again, thanks a lot for your attention and have a good day.
Whoa, that was a quite an interesting talk. Thank you very much, Nicolas. Quite interesting. There are some questions already for that, because you said in chat there are no questions, but I'm quite interested in this. You described it at the beginning to read this log more likely as a hack. I know CDC and Debezium is in development for quite a while. Would you really say this, what you showed us, it looks like this is a lot of already ready-to-use library. Is this a production-ready approach? And if yes, would you recommend this, or what would you aim for? I know it's always depending on the problem you're facing, but generally, would you say this is a totally feasible approach and you would recommend anybody to take a look at this?
So first, this is a feasible approach. This is production ready. And actually, you have Gunnar Morling, who is there in the conference and is behind Debezium. Now, depending whether it's like you should use it, as you mentioned, it depends. But if you want to solve this problem of like caching being not in sync, I think this is a very good approach, actually.
Okay, cool. Just on the side, you have more contact with the CDC approaches, etc. So I always hear people when they talk about CDC, mainly talking about Debezium for the Java world. Do you know of any kind of familiar libraries or libraries trying to solve the same problem in a similar way, or something comparable, alternatives?
I don't know of anything else, but for example, you will probably need other alternatives if you are in the cloud, because the cloud, I mean, you don't have access to the log. I know that some cloud providers provide you also with events, so you can subscribe to events and you can do the same. Of course, it might probably be a bit slower. So the window of not synchronization, I mean, the window of like eventual consistency will be longer, but still you will achieve the same. So you just need to be aware of your environment and use the way to get the events. That's the most important stuff.
Okay, thank you. Cool. Chat, if you have questions, feel free to ask. We are monitoring the Q&A section and the chat heavily. I have more likely one also, how to say, depends on question. So you talk about this Evergreen cache, and we fixed the problem of the TTL somewhat with that. But regarding cache eviction, regarding the eviction, it's always a depends on problem. But what way would you go with when you have? Because I think it changes the way of the caching a little bit, because it's not anymore about how to say, I'm really missing the words, but I think it changes the problem a little bit regarding eviction. What kind of process would you recommend then to use?
Because I think this is another issue. Eviction is another issue. I mean, I always tell people, hey, like, you probably want to use a cache. The first thing that you do is use a hash map, especially if you are a junior developer. I mean, I did it before. So the cache gets filled, and then the memory gets filled, and your cache competes with your own application. And at some point, you've got an out of memory error. So the idea is you need to set a limit. And in that case, you need eviction. So I believe this is a separate problem that is completely orthogonal. Yes, you remove stuff from the cache, but for other reasons. You remove stuff from the cache because your cache is full.
Yeah, that's true. But how do you react in combination with? Because I understand your point, but I still think that CDC somehow changes this a little bit. Because normally you have a hit and miss, you have your TTL, and you're removing objects. So you normally have, let's say, more time. No, maybe I take a little wrong approach, because I thought I can eliminate TTL in the cache with this Evergreen cache, but most likely it will not be a good solution to remove TTL anyways, because the cache needs some refreshing over time. Or what is your take on that?
Okay, so like it really depends. In some, like if you are a big company with a lot of money, you can have like very huge caches, and in that case, you have so much money that you value more the speed of your whole processing pipeline, whatever it is. So you can put your whole database in the cache, and then again, you don't have this problem of eviction because you put everything in your normal database in the cache. It's very, very context dependent. But yeah, regarding eviction, for me, this is an orthogonal concern. Those are two different separate concerns.
Okay. I have one more question from my side, because I'm really, really curious regarding this cache implementation. You talked about the pitfall that the pipeline, when it's not running, you have problems. But are there any other common pitfalls you know from CDC-like approaches, which most developers fall into a trap or something during development?
I recently read a North article that was about like one architecture involving the Bayesian and Kafka and everything to implement the Saga pattern. And at the end of the article, they were like, that was really something really nice, because I never happened to read that stuff before, is what happens if that fails? And that's very, very important, because here I'm talking about the happy path. But yeah, you should always be careful about what happens if it fails. in the happy path, everything works, that's fine. But especially in distributed systems, we should be very, very careful. Like this component, if it fails, what will happen? Okay, if it fails, and when it starts again, then the pipeline resumes as normally, then everything is fine. I just lost time. Perhaps I got more events to handle, and perhaps it will create issues afterwards. So when you start again your pipeline, you should throttle it. This kind of stuff. So I'm not aware of anything specific, but if you are doing architecture, you should always be careful to pinpoint every component that can fail and what problems you will have. That's, I mean, you know, that's like when you write Java code. The happy path is easy. The catch blocks are the ones that you really need to think about and to make sure that, even in that case, you will end up in a consistent state. Or you can accept inconsistency, but I mean, you should have like procedures in place to say, okay, I accept inconsistency, and what can I get to make it better afterwards? Is it manual? Is it automated? This is the kind of stuff that you need to think about.
Okay, that's a really good tip, by the way, to think about the not happy path. We have a question in chat from Radoslav Netkov. Sorry if I pronounced the name wrong. How the cache would work for complex queries over multiple tables with 1-to-n relations?
That's the problem of the cache. In general, a cache is just a single key value store. That's not an issue if you are able to get the events from different tables, to order them, and during your pipeline to transform them, to aggregate them into a single entity and put them into your cache. Of course, when I say it's very easy. When you need to implement it, it will be hard because, well, the problem is in that case, you will probably have the issue of getting the events out of order. So probably in that case, you should put everything into a single Kafka topic and then read from that Kafka topic, and then that your pipeline is smart enough to reconstruct a single entity that you can put in the cache from multiple records from the table. It's possible. It's a bit much more involved, but it's theoretically possible. However, I would suggest, if it's possible, to avoid that kind of problem, because it makes your system much more complex and in that case a bit more fragile.